All right, for today we are going to look at attributes of a function. How can we describe a function graphically? First attribute we're going to look at is symmetry. Is my function symmetrical along the y-axis, symmetrical along the x-axis, or symmetrical along the origin? Now there are two ways to test for symmetry. One is to take your function and basically graph it. And looking at this graph, can you tell me how is this function symmetrical? Along which axis?
Y.
The y, right? If I take it and rotate around here, or like a piece of paper, fold this function across the y-axis, I see that the left side will fold right onto the right side. That's more or less the definition of symmetry. Now you can also test this algebraically. And to do that, you substitute negative x for x. And then simplify. Do you get the original equation back? So what I mean is y minus x squared plus 5. Let me substitute a negative x for my x here. So I get negative x squared plus 5. And now I need to simplify. So that's y equals negative x times negative x. And somebody tell me, what is negative x times negative x? Positive x squared. Y equals positive x squared plus 5. Is that my original function? Yes. So that is a way to algebraically test to see if something is symmetrical along the y-axis. It passes through this. Now if you note, there's only one type of function that will pass. Notice I had an even number of negatives, right? A negative and a negative makes it positive. So this number here, as long as it's as long as it's even, it will create a positive value. You'll get your original function. Now note, that is just it's not a guarantee, it's just a quick reference when you want to start off. I see a 2 that's even, I'm thinking it's symmetrical along the y. Because I can shift this graph to the right, put it here. Tell me, is this symmetrical on the y? No. It's still even because it has an even power, but it's not symmetrical. So don't take this as a guarantee, just as a quick, okay, I'm looking for y symmetry, maybe. I would definitely graph it or test algebraically. Next is symmetrical along the x-axis. So like I were to fold my graph along the y, I'm folding it along the x-axis here. So does my top part, when I fold it along the x, fall exactly onto my bottom part? In the case of this circle, yes it does. And to test algebraically is instead of substituting a negative x for x, you substitute a negative y for y. So I have x squared plus negative y squared equals 4. And now simplify. That gives me x squared plus what?
Negative y, or y.
Yeah, plus y, right? That negative turns into a positive equals 4. And is that my original function? It is. So this is symmetrical along the x-axis. Now note, anything that is symmetrical along the x-axis is not a function. Why?
Oh, because there's more than one value.
Very, one value for x. Okay, very good. So yeah, if I do my vertical line test, how many times does my graph hit my magenta line here? Twice, right? That's the same as feeding 2 pieces of paper in a printer at the same time, which is a big no-no. You get a paper jam. So this is not a function. In fact, anything that is symmetrical along the x is also not a function. It will always fail that vertical line test. So we won't see too much x symmetry, x-axis symmetry. One more, I can be symmetrical along the origin. Now how that works with the paper fold is that you're taking your graph, you're folding along the x, and then you're going to fold it along the y. So notice, if I have a graph down here, I'm folding along the x, it ends up right here. Then I fold along the y, where does it end up? Right here. So this is an example of an origin symmetry. It's a double fold. You can also think of it as use the origin as your pivot point and rotate this 180 degrees, where do you end up? Where this other side is. Now, if we're making a double fold, then to test this algebraically, we need to substitute both x and a y for a negative. And does it come out the same? So I have y, I'm substituting a negative y in for y. X cubed, I'm substituting a negative x in for x, and then cubing it. Do I get my original function? Let's see, negative y equals negative x times negative x times negative x. These two make a positive x squared, right? And what is x squared times a negative x?
Negative x cubed.
Very good, a negative x cubed. And I have a negative y there. Now I need to make this a positive for y. So I'll multiply this by a negative, which turns that positive, and multiply the other side to a negative, which turns that positive. Do I end up with the same function?
Yeah.
I do. So to test through the origin, you're going to either do a double fold graphically or a double negative with both your x and y algebraically. Now note, this will only work out because I have an odd number here. Odd means I'm going to have a negative left over, correct? Meaning that negative will also cancel out with the negative I have attached to my y. Or at least it should. Again, I can transform, move this graph here. Is that symmetrical along the origin? No. So again, I would verify graphically or algebraically and not just take the highest degree. Just word for it. So there is y, x, and origin symmetry. About y and origin, like I mentioned, if you see it symmetrical along the y-axis, and it is, then it is also called an even function. Note, it'll always have some even power here for the highest degree. Even powers are not always symmetrical, but if it is symmetrical on the y, it is always an even function. Does that make sense? Because I can turn this into x minus 1 squared, or my highest power is squared, which is even, but this means I shift it to the right, which means it is no longer symmetrical along the y. And then likewise, if it's symmetrical on the origin, then it is also called an odd function. And if you notice the highest power of that function, it should be, and will always be, if I can get this going on, an odd number. There we go. So origin starts with the letter O. Odd starts with the letter maybe that'll help. So if not, you can look at the highest power. Is that even or odd number? One more thing we want to look at is increasing or decreasing. Yes, there's a constant, but since we're dealing with functions and most of our functions have curvatures, they won't have constants, you won't be seeing this too much. So let's look at increasing and decreasing. Let me make this comment. How do we read books? We read it from what to what?
Left to right.
Left to right. That's exactly how you need to read math as well. So when I'm trying to read increasing and decreasing, I need to read from left, which is negative infinity, to right, positive infinity. So as I look at my graph here, from left to right, what's going on with my y value? It's increasing, right? It's going up. So that is increasing. What's going on with your y? How is your y changing? As I look at this graph here, as I'm reading this from left to right, what's happening to my y value?
Decreasing.
It is decreasing. So my graph is going down. So, our example. Notice when you have your intervals, they should give you the totality of your domain. You should be able to put these all together, increasing and decreasing, and it will give you your whole domain of that function. So what this is intervals is part of your domain. So which part is my graph increasing?
0 to infinity. Wait, no, that's not 0.
0. Okay, so one thing to note. Tell me, what is the point where my graph changes from increasing to decreasing? 0, right? 0 right here. As far as the x is concerned, it's 0. But the actual coordinate is 0, 5. Sure, we'll go with 5. That is my turning point, if you can remember from Algebra 2. My point where my graph is going to change in its intervals. Before this turning point, from negative infinity to 0, what's going on?
It's decreasing.
Very good. It is decreasing. So my interval for decreasing is from negative infinity to 0. Oops, not sure what I was going to do there. To 0. Which means from 0 to infinity, what is my graph doing?
Increasing.
It is increasing. So it's increasing from, oops, let me put bracket there, from 0 to infinity. Notice if I take these two and add them together, I get from negative infinity to positive infinity, which is the domain of this function. So I'm splitting up my domain in terms of increasing and decreasing. So see what I'm getting at when I say that? So most important thing with increasing and decreasing, remember where you go reading from left to right. My graph isn't, it looks like it's increasing, right? If you start at the vertex and go out like this, well, both sides are increasing. But that's not how you should be reading this. You should be reading it from left to right. And I see here is it decreasing, stops, turning point, then increase. All right, so while I take attendance, let me have you answer these two problems. 1 and 2, we need to identify whether the function is symmetrical or where it's symmetrical. Determine if the function is even, odd, or neither. And at what intervals is the function increasing or decreasing? Number 1.
It just has a test. It doesn't have a review.
F of x equals negative 3x squared plus 4. Determine whether the function, where it's symmetrical. So let me look at the graph. How is this function symmetrical? The y, right? Okay. So this is symmetrical along the y-axis, which means it's what kind of function?
It's not.
Even, odd, or neither? It's even. And what are my intervals for increasing and decreasing? So tell me, from negative infinity to where? 0, it's doing what?
Oh, I was right. I just did it backwards.
From negative infinity to 0, it is increasing. And then from 0 to positive infinity, it is
4 to.
decreasing. So you would put increasing, negative infinity to 0, and decreasing from 0 to positive infinity. Those are my intervals. Now number 2, f of x equals 2x cubed minus 4x. So let me look at my graph here. Tell me, how is this graph symmetrical? Along the origin, right? If I take this pivot point, rotate it 180 degrees, I'll get this other side. Or if I rotate it, let's say if I make it symmetrical along the y, I get kind of an M here, and then flip it along the x. That M curve, oops, flips over like this, if you can visualize that. So this is symmetrical along the origin, which means it's what kind of function? It's odd. And now let's look at our intervals. How many turning points do I have here on this graph? 2. From negative infinity to this point right here, my graph is doing what? Increasing. So again, left to right, it is increasing. From that point to my other turning point, between here and the orange, what is it doing? Decreasing. And then from that point to positive infinity, what's going on? Increasing. So here's kind of a visual way to see in intervals. Everything in the green is increasing, everything in the orange is decreasing.